Good afternoon. My name is Wenjun from Tianjin University. The title of my presentation is an electrochemical biosensor enhanced by surface acoustic waves for point-of-care testing. Now today, the presentation will be divided into 4 parts. First is the background. Point-of-care testing is a real-time detection technique with the advantages of simpler operation, lower costs, and higher efficiency. Therefore, it is widely used in the environmental monitoring and biomarker detection. Now, the POCT system mainly achieve measurements through the electrochemical and immunological methods, using the devices such as the paper-based assays, lateral flow assays, and microfluidic chip. But there have some limitations, such as long testing times and almost quantitative tests, the uneven distribution, and inconsistent flow. However, the adequate mixing and reaction are the prerequisites for the sensitive detection. Therefore, the rapid response and high sensitive detection are key requirements for the point-of-care testing. Now, the electrochemical sensors-based POCT system can achieve quantitative testing, and with the advantages of miniaturization, easy integration, and automation, which is suitable for the continuous monitoring, and making the POCT system integrated within the electrochemical sensors a promise. Now there have some studies. The nanomaterials is almost used, but the inconsistent modification can lead to the signal drift and automation. The passive and active external driving can also improve the sensor's performance, but the passive driving consumes more samples and costly. In contrast, the active driving with the energy conversion offers more controllable ways. The ultrasound actually is frequently used because of its non-invasive, easy integration, and fibrillation. In the research field of the ultrasound, the low-frequency ultrasound resonator is commonly used, but the variation it results can corrode the electrode, and the high energy it requires always affects the bioactivity. The high-frequency ultrasound resonator can induce the fluid motion without the variation, but the ultra-high frequency resonator always uses the high position, which is limited by the technology and the fabrication. So the high-frequency resonator, such as the surface acoustic waves, it is similar to operation and have low impact on the biomolecules. Therefore, this study proposed an electrochemical glucose sensor enhanced by the high-frequency source. The second part is the enhancement mechanism and the sensor design. When the high-frequency signals applied to the interdigited transducer, the piezoelectric substrate undergoes vibration, and the vibration propagates along with the substrate of piezoelectric substrate, forming the source, and the source diffracts into the solution. Its energy is absorbed and converted into the kinetic energy, forming the acoustic streaming. The overall design of the sensor includes 3 parts: the additives, and the electrochemical 3-electrode system, and the microfluidic chips. The 2 asymmetrically placed additives generate the source that propagates into the solution, exerting interfacting forces on the solution and inducing clockwise vortex motion, facilitating a rapid mixing in the reaction cells. And the 3-electrode system performs the electrochemical detection. When the source applied, it can accelerate the arrow moment, thus enhance the diffusion rate, and it can also speed up the transfer rate of the transfer process of the analyzed solution to the surface of the working electrode. So it can improve the electron transfer rate and the current response, which in turn boosts the sensor sensitivity. And this is the structure diagram of our sensor. By using this design of the additives, our sensor can have a better piezoelectric conversion effect. And our sensor is fabricated by the standard MEMS process. The red picture is our sensors. The third part is the results. First, we studied the acoustic streaming through the simulation. From the results, we can see that the source generates a clock vortex in the cells, and the higher the input voltage, the faster the flow rate, thus enhance the diffusion rate. And by capturing and analyzing the flow field, we can see that the solution indeed generates a clock vortex. Next, we verified the effect of source on the diffusion rate. By fitting the results at different scanning rates, we can see that the peak rate is linearly related to the square root of scanning rate, indicating that our reaction is only controlled by the diffusion. And we also test the effects on the oxidation and reduction current. We can see that the current ratio varied minimals, showing that the introduction of source actually doesn't affect the reversible process of electrochemical detection. But the oxidation peak current increased, indicating that the source allow more current to flow through the working electrode. And what's more, the diffusion efficiency increased by 41.24%, confirming the enhancement effect of source on the diffusion rate. Next, we test the response time. First, we select a relevant working potential and test the response time. It can be said that it can be reduced to about 5 seconds. And next, we also test the sensor's sensitivity. From the current curves of the sensors at different concentrations, we can see that the gradient measurement can be achieved. And from the fitting results, the sensitivity can be increased by about 37.7 times. Next, we verified the effects on the mass transfer rate by the impedance measurements. This is the Nyquist plot. By using the covalent circle model, we can get the red table. From these results, we can see that the solution resistance decreased by 29.33%, and the charge transfer resistance decreased by 31.16%. All these results showing that our source can effectively enhance the mass transfer rate. By confirming the effect of the source, we applied it in the glucose for the biosensing. In there, we also test the response time, and we found that it can also be reduced to about 5 seconds. but their sensitivity is increased by 17.34 times. Finally, we test the activity of enzyme by detecting the hydrogen peroxide. Since hydrogen peroxide is an intermediate of the glucose decomposition. From the right finger, we can see that the activity of the enzyme decreased with the increase of the input voltage, but it has little impact. So it shows that our sensor is suitable for the biosensing. The first part is the conclusion. This study proposed an electrochemical glucose sensor based on high-frequency source, investigate and confirms the enhancement mechanism, and then environmentally verified the effectiveness of the sensor for high position detection of low concentration glucose. Finally, I will show my graduate to the Laboratory of Bioinformation Measuring and Biomanufacturing of Tianjin University.
Right.